Hi, now let's discuss about the evaluation test for disease diagnostics. Let's say as a biomedical engineer, you're developing a new test or new instrument, bioinstrument, which will diagnose the disease. Then you must consider about the accuracy and precision, and at the same time, so-called sensitivity and specificity you have to report to get it approved. So this is a very important concept to know if you want to make your instrument to be able to out in the market. So let's first discuss about the sensors used in biomedical instruments. So there are different kind of sensor types, which is a thermal sensor, mechanical sensor, electrical sensors, and chemical sensors, and optical sensors. And there will be sensing element, and I'll give you some example. So first, thermal sensor. The sensing element, you may have heard about a thermocouple and also a thermistor. So let me have an example of the electronic thermometer, which measures our body weight, body temperature. And second, as a mechanical sensor, those sensing elements could involve a strain gauge, which I will discuss further, and or piezoelectric sensor. So piezoelectric is a kind of a displacement or pressure can give rise to a voltage. So here's an example as I put this piezoelectric transducer, which when we apply voltage, then this piezo will have a change. So in this case, a changing in displacement. So an example as a pressure transducer, one type of pressure transducer I actually used is a piezoelectric, so that we measure, let's say, gas pressure in a specific vessel. There's a specific gas, and I want to measure the pressure. We have a piezoelectric transducer that measures this pressure, gives rise to a voltage difference, and that we can measure. So that's another example of pressure transducer. You see, transduce means converting one type of signal into another form. And thirdly, electrical sensor, one example is electrode. For example, like electrocardiography, and that's like this. We have already discussed these electrodes are sensing the electrical activity of our heart, because the heart's cardiac myocytes generate electrical field and electric vectors. And chemical sensor, an example as a sensing element, we can also use electrode, especially a good example is a pH meter, which looks like this. Many laboratories have this. When you are preparing a solution with a certain pH, then you have to use this pH meter to measure the pH, and these are the electrode. And lastly, I want to discuss about optical sensor and sensing element, which measures the photon, the amount of photons or light. So a typical one is so-called a photodiode, which is cheap and broadly used. And the other more specialty ones are photomultiplier tube, which is very, very sensitive, even giving us a single photon sensitivity. So we'll discuss more about this. And what are the examples of this optical sensor? And one of the vital sign and important ones, pulse oximeter. Now, a pulse oximeter uses a light to having this transmitting through our, let's say, biological tissue where there exists a blood vessel, so that we can measure the oxygen concentration, saturation of the oxygen in the tissue. Okay, so now let's discuss about when we develop a new diagnostic test. Let's say we have this machine which, let's say, measures some body fluid of patient, and it gives out a result saying that, hey, you've got this disease or you are free from the disease. then how can we characterize the performance of this diagnostic test? So for this, people have developed a very simple decision matrix. So decision matrix is about like this. So first, in an absolute sense, like the patient will have this disease or no disease. So that's what we ultimately want to know. However, that's not very easy to figure out. So we develop an instrument, or bioinstrument, which spits out the result as a value, quantitative value, that we will, based on this value, we will say, hey, this is a threshold and you are higher than this value, hey, you are positive, which is like from our test, or below, that's a negative. So positive and negative of our disease test results and the absolute sense of disease present or absent. And with those 2 by 2 table, we can now characterize our performance of an instrument. So here you see disease present or disease absent, and disease and no disease. While test side, we can always set certain criteria and having it as a test positive or test negative. That with this, what we can say, what we are interested in, what the true disease or not. So having disease and getting positive means true positive. Make sense? And having no disease and getting negative is true negative. So these are like the true estimation. And while there are other cases, having, I don't have a disease, but somehow this test result giving me damn positive. So that's false positive. Okay, but I do have a disease, but this machine is not good enough to giving me a negative. That means a false negative. Does that make sense? So this is very simple decision matrix, which gives us to define more specific performance metrics. So for this, like we can say, like everything, every case is disease plus no disease, right? Or we can say there's only positive or negative. So all the positive plus negative, which means all these 4 elements sum together. So true positive, false positive, false negative, true negative. So that's all. And what are the positive? So positive is true positive plus false positive. Okay. What are negative? True negative plus false negative. What are the disease? So disease can compose of true positive plus false negative. Likewise, no disease will be composed of false positive plus true negative. So with this, we will define more specific parameters.